Welcome to my thesis presentation titled Active and Physics-Based Human Pose Reconstruction. The outline of the thesis will be as follows. First, I'll introduce challenges in 3D human pose estimation. Then I'll give a brief overview of the tasks studied in this thesis. Next, I'll show the papers, including the thesis and their associated research question. And then I'll in turn present the contributions to each research task studied in this thesis. And then finally, I'll end with some concluding remarks.
A typical example of 3D human pose estimation is the case where a normal monocular image of people is given and a deep neural network predicts the body poses and often shapes of the subjects in the image. However, despite amazing results, state-of-the-art neural networks tend to make mistakes that usually become evident at closer inspection. The reason is first and foremost that the problem is ill-posed as we attempt to recover an articulated 3D structure from a 2D image. This leads to, for example, depth ambiguity problems. Furthermore, humans greatly vary in their appearances, body types, and they may take many different body poses. Another great challenge is that of occlusions and partial visibility. When people are partially occluded, the neural networks must either rely on priors or omit the missing body parts. Finally, collecting annotated 3D human pose training data usually requires expensive motion capture equipment, and capturing data for all types of motion, body types, and camera angles is both expensive and practically infeasible. As a result, state-of-the-art pose estimation networks tend to make mistakes as seen above.
My thesis studies how to improve visual perception with an emphasis on 3D human pose estimation in three distinct ways. Firstly, in active human pose estimation, an intelligent agent is given a pre-trained pose network and should move intelligently to reconstruct the subject in a scene. The task is essentially how to learn to avoid occluded views and to mitigate camera viewpoint biases in the underlying pose network. Next, in embodied visual active learning, the embodied agent is given an untrained visual model in a novel environment and must learn how to refine it. The idea being that agents must be able to adapt to novel percepts as no training data is likely to be complete. In the paper, we study the problem for semantic segmentation, but refining a visual model in the presence of novel view is an idea that is of interest to other tasks such as object detection and human pose estimation. Finally, physics-based human pose estimation augments 3D human pose estimation from video with a physics simulator to enforce constraints and increase the richness of the output through, for example, torque and contact force estimation. The three tasks are studied in the 5 papers of the thesis as well as the 2 follow-up works not included in the thesis. Paper 1 and 2 studies viewpoint selection and attempts to answer how an active observer should learn to seek out informative viewpoints and when it has gathered enough information. Paper 3 studies embodied visual active learning to answer the question how an active observer may learn to refine its perceptual system. And finally, paper 4 and 5 studies physics-based human pose estimation and answers how physics can be integrated into the reconstruction process and how differentiable physics may utilize to make the process more efficient. Let's now explain the 3 areas more in depth, and let's start out with active human pose estimation. The motivation behind active human pose estimation is very natural. Imagine an agent is given an image of 3 people. Using a 3D human pose estimator, it may predict their poses. However, as the man on the left occludes his left arms and the legs are outside of the frame, this might lead to errors in the reconstruction. In the standard human pose estimation task, recognition is separate from movement, and the images are considered given and the agent is locked in place. In active human pose estimation, we combine recognition with active exploration to allow the active observer to move to other viewpoints to better observe the subject. Thus, it may move to other viewpoint that provides it with new and complementary information that helps it reconstruct the subjects in the scene. So the task is to learn an agent that selects good viewpoint, good in the sense that they yield low error reconstruction of the subjects in the scene. Furthermore, selecting too many viewpoints is both computationally inefficient, and some viewpoints might even hurt the reconstruction due to noisy estimates by the underlying pose estimator. In order to enable reproducible experiments and to focus on viewpoint selection strategies rather than controlling and interfacing with a physical robot, we emulate an active observer using the CMU panoptic dataset. It is a multi-camera dataset with recordings of people interacting with each other. The time-synchronized cameras are mounted in a spherical dome encapsulating the scene. when we then simulate an active observer by allowing the agent to change viewpoint by switching between different cameras. Let's quickly look in detail of how the task works. At the first time step, the agent is given a random initial viewpoint on the camera dome, indicated by the green arrow. Using the egocentric view of the scene, the agent should make a decision. It may choose either to select a new viewpoint or to move on to the next time step. Let's assume the agent decided to view the scene from another viewpoint in order to improve its reconstruction quality. The move action is applied to the environment, and the agent is now given the new viewpoint as input. Using this observation, it must again decide if it has acquired enough information or if it should terminate the viewpoint selection for this time step and move on. Let's assume the agent decided it has observed the scene sufficiently and it selects the done action. It should then integrate all views for that time step and produce a 3D estimate of the people in the scene. After each time step is reconstructed, the environment progresses to the next time step t = 1, and the previous steps are repeated again until the entire video is processed. At the end of the sequence, the agent has produced 3D estimates for each time step. The goal of active human pose estimation is to minimize the mean per joint 3D reconstruction error across the entire sequence. In my thesis, 2 methods are proposed for solving active human pose estimation. In paper 1, we equip a reinforcement learning model with a 2D pose estimation network. It is then trained to select viewpoints such that it sees every person from at least 2 cameras so that they may be triangulated into 3D. Hence, the stopping condition for each time step is a heuristic rule that each joint should be observed from at least 2 cameras, which is the minimum number of cameras required to triangulate a point in 3D. We formulate a self-supervised reward based on 2D reprojection errors, which allows us to train the RL agent without any 3D annotation. In paper 2, we study the problem of an agent equipped with a 3D human pose estimation network instead of a 2D network. We again train an RL agent that learns to select informative viewpoints and fuse multiple 3D pose estimates together. Since 3D pose estimation usually predicts the entire pose regardless of occlusion based on learned priors, we do not use a heuristic stop. Instead, the agent learns to stop viewpoint selection when it believes it has observed the subjects from sufficiently many viewpoints. Since the 2 approaches are similar, and in order to conserve time, I will focus on the model in paper 2. The schematic figure of post-GRL is shown on the slide. On the left, we see the panoptic camera dome from which the current selected camera provides an RGB image. This image is then processed by a pre-trained and interchangeable 3D human pose estimator that our agent uses to reconstruct the poses of the subjects at each visited viewpoint. The predicted poses and feature map from the 3D human pose network are given as input to a policy network that is trained using reinforce. The policy then predicts either how to move relative to the current view in the form of relative azimuth and elevation angles on the spheres. The policy may also select the binary done action to indicate that it is done with the reconstruction of the current time step. We evaluate post-RL in 2 modes. Either the single target mode, where it should only reconstruct a single person and all other people are considered as occlusion, and the multi-target mode, where all people in the scene should be reconstructed simultaneously. Here are qualitative examples from the single target setup. The agent receives an initial view in which the target in the red box occludes his arms and the legs are outside of the view. As a result, the reconstruction of the arms and legs are poor. Next, the agent moves to another view where the legs are visible but the arms are viewed from a difficult angle. Finally, after a third camera, the reconstruction of the arms has improved and the agent decides to stop the viewpoint selection. In this multi-target example, three persons, the initial view contains only the first target from a poor viewing angle, producing a poor estimate. The agent moves to a second viewpoint, exposing the 2 others. The man in the green box is far away, but otherwise fully visible, while the 2 others are seen from behind with legs and arms either missing or self-occluded. The third viewpoint exposes the legs of the purple man, while the green man is seen more clearly, thus improving their estimate. Finally, in the fourth view, the blue woman's arms are visible, the green man isn't detected from this angle by the pose estimator, and hence his pose isn't updated. At this point, after having seen all targets from multiple viewpoints, the agent decides to stop the viewpoint selection. Now let's have a look at the quantitative results for pose RL on the panoptic dataset. Let's start by looking at results in the single target setting. The y-axis shows the mean per joint 3D reconstruction error, and the x-axis shows the number of cameras selected. The baseline has no learned stopping, so to fairly compare, we evaluate the model and the baseline at fixed number of cameras per time step. We see that our agent in blue outperforms both the random and max as in baselines shown in red and yellow respectively. The latter is a strong baseline that selects cameras in order to spread them out maximally to cover the scene. For the agent, we also plot the average number of cameras selecting using its learned done action, but dynamically selects the number of cameras for each time step. The average of this is marked by the dashed line in the plot. As can be seen, this is superior to using fixed number of cameras, especially for the single target case. The agent thus manages to budget its computation depending on the situation, selecting more views for complex time steps and fewer for simpler scene. Shown in purple is also the cheating oracle that selects cameras based on 3D error and thus acts as an estimate of the lower bound error. The second plot shows the multi-target case. Here, the agent again outperforms the baselines, though the done action has a much smaller impact. We believe this is due to the fact that when reconstructing a large number of targets, the occlusion and difficulties of the target pose configurations are average, thus making the number of cameras required per time steps more consistent. In other words, to reconstruct all subjects, you need to select a larger set of cameras so that each subject is covered from a good viewpoint. Note that the agent learned to stop roughly when the error curve is flattening out. The final plot shows the runtime of the model compared to the baselines plotted in log scale. The x-axis is the runtime in seconds, and the y-axis is the runtime in seconds, and the x-axis is the number of selected cameras. The agent's policy requires little extra time in comparison to the baselines, comparison to the pose estimator, which makes the agent and the baselines almost equally fast. This, however, is not true for Oracle, which needs to evaluate all cameras to compute a respective reconstruction error in order to select cameras in order of ascending error. Now let's move on to the second part of the thesis, which is on embodied visual active learning. Recently, there has been a surge in embodied tasks in computer vision. The shared property is that they study the development of intelligent agents that act with a simulated physical body. For example, an embodied agent may be tasked to navigate a simulated house using image and depth as input, with the goal of finding an object such as a stool in the example below. Active learning, on the other hand, is the idea that all training data isn't equally useful or representative, and by intelligently selecting a good subset of training examples, we can train a high-performance learning algorithm using less annotations. In computer vision, annotations are often expensive, so intelligently selecting what to label reduces cost and may also focus efforts on instances which are particularly tricky for the learning algorithm. So in the example below, instead of annotating a huge dataset, we may have an algorithm select only those examples which it think will be most important and beneficial during training. Active learning then studies how to design such a label querying algorithm. So the third paper of my thesis introduces the task of embodied visual active learning, where we combine embodied AI with active learning. Here the agent explores a novel environment in the form of a simulated house. The agent may request annotations from an oracle and use those to refine its perceptual model, which in the paper takes the form of a semantic segmentation network. In some ways, this can be thought of as an extension of the ideas in part 1, where an agent had a pre-trained visual model and learned how to look around the scene to better negate estimator biases and overcome occlusions. It essentially learned how to get the maximum performance out of a pre-trained visual model through exploration. In this task, the agent explores the scene in order to learn its visual perception model in the first place. And while the paper studies the problem for semantic segmentation, which is a task with very expensive per pixel annotations, the idea of embodied active learning is applicable to other vision tasks such as human pose estimation or object detection. At a high level, the task is presented below. The embodied agent explores a 3D environment and receives the current view as an observation. The observation is then processed by its perception model and passed to the agent so that it might either request annotations for that observation or select a movement action to explore the environment further. Let's have a quick look at our proposed method. The embodied agent moves around in a 3D environment in the form of a virtual house. The agent is controlled by neural network policy, but is trained to explore the house in order to seek out informative views on which to refine its semantic segmentation network. The policy is trained using the PPO reinforcement learning algorithm, and the RL reward function penalizes requesting annotations from the oracle and rewards exploring its environment. At the end of a trajectory, it is given a reward proportionally to how much the semantic segmentation network has improved. The agent may either select a movement action, such as move forward, rotate left, etc., or a so-called perception action in order to refine its semantic segmentation network. Selecting a movement action updates the position of the agent, gives it a small positive reward that encourages exploration, and propagates the latest ground truth annotation using optical flow. Propagating the annotation allows the agent to get a bit more use out of each annotation. The input to the policy is an RGB image of the current view, the predicted semantic segmentation mask from the semantic network, and the optical flow propagated annotation. There are two types of perception action. The annotate action, which requests a ground truth semantic segmentation mask for the current view from the oracle, and then adds it to the training data for the semantic segmentation network. And the collect action that adds the currently propagated annotation mask to the training data. To encourage that the agent selects only meaningful views to annotate, we penalize the annotation action during our training. The collect action, on the other hand, requires no extra annotation and hence is not penalized. After each perception action, the semantic segmentation network is refined on the new data. Let's look at quantitative results on the photorealistic Matterport 3D simulator. On the x-axis, we have the number of actions taken by the different methods we have proposed, and on the y-axis, we have our MIOU score, where higher is better. The top blue line is a space-filling curve method. This method requires knowing the layout and reachability of the environment in advance, and hence has an unfair advantage compared to other methods, and it is included as an upper bound method. Compared to our learned agent, it achieves a better score after 256 action, but it also uses 32% more annotations. Compared to other non-cheating baselines, the learned RL agent is better in terms of both MIU and the number of annotations required. For example, it uses 31% less annotations than the closest baseline in green. In the next plot, we look at the number of annotations versus MIU for the methods. Here we evaluate how well each method learns to understand its environments given n annotations. We see that ordering between the methods remain the same as in the first plot. We also note that the agent is as efficient or more than the baseline for less than 15 annotations. This is interesting as this is roughly the number of annotations performed during training. That would suggest that the agent learns a strong exploration technique to start out with, but doesn't learn as a good exploration technique for longer trajectories, especially compared to systematic exploration methods like the space filling curve. Finally, it's time to cover the last part of the thesis, which focuses on physics-based human pose estimation, where we integrate physics to improve monocular estimation from video. While deep neural networks have achieved astounding results, they tend to make predictions that are non-physical. In this video, the character is moving away from the camera. The 3D pose network produces results that project correctly into the image, but when looking at the motion from the side, we see that the character is not walking, but it is actually floating forward. Another use case for integrating physics is to estimate physical attributes such as forces and torques directly from video. As a tangent, physics can also be used to forecast motions dominated by physical forces, such as when gravity pulls someone to the ground as they faint. This can, for example, be used to generate synthetic training data. Finally, integrating physics provides a natural way to enforce physical constraints such as body torque limits and thereby constraining the reconstructed motions to be physically plausible. The approach we take to physics-based human pose estimation in paper 4 is presented on this slide. The input to our method is a standard monocular video of a person, for example a person doing a judo roll. The kinematic step first estimates the per frame 2D key points, 3D body poses, semantic body masks, and body shapes. We then use high confidence frames to compute a temporally consistent body shape. Our method assumes that the camera is static, and that using that assumption estimates the ground plane location. Finally, we perform optimization to refine the poses. The goal is to produce temporally smooth poses and place the motion on the estimated ground plane. The resulting optimized motion becomes the visual evidence for the physical optimization. Next, we generate a physical body model which approximates the statistical body model estimated from video. Finally, we perform trajectory optimization to recover a physical motion which should be as close as possible to the observed visual evidence while being constrained by the physics of a simulator. Of our physical optimization, which essentially is a type of trajectory optimization. We first define the initial state, which describes the scene, for example any objects in the scene and the ground plane location, as well as initial pose of the body. For each frame of the video, we input body torque values to move the character. We limit each joint to plausible human torque values. Using a full-featured rigid body simulator, we compute the resulting forces and torques under contact constraints when applying the input body torques to our physical model. This yields a frame of physical motion. We then compute a set of losses between the visual evidence obtained using the kinematics and the physical motion resulting from the simulator. As the physical motion is constrained by the laws of its simulated physics, the resulting physical motion should be physically plausible and, for example, not float unrealistically above the ground. This process is repeated for each time step. We then optimize the torques in order to minimize the sum of the reconstruction losses using the gradient-free CMAS method. Let's look at some qualitative example. This is the video from the first slide. Again, the character moves away from the camera, which leads to ambiguities, which in turn causes the floating motion in the kinematics in the top row. This is then corrected by physics in the bottom row. Here are some examples of physics-based reconstructions from internet videos with unknown camera parameters for dynamic motions. Notice how our model supports full body contacts in the left bottom corner. We evaluate our method on 4 sets of videos, 3 studio capture datasets, and then real-world internet videos as seen before. Comparing the full results with physics to our kinematic initialization, that is what our first step produces, we note a slight reduction in joint error and a significant reduction in velocity error, as well as physical artifacts such as foot skating. The final paper addresses the high computational complexity in paper 4. This stems from the fact that it uses a non-differentiable physics engine and resorted to minimizing the loss using gradient-free optimization techniques that tend to be slower than their gradient-based counterparts. Paper 5 introduces the first physics-based human pose estimation approach that integrates a full-featured differentiable physics simulator into the reconstruction process. We may then optimize the loss using the gradient-based BFGS method together with Bayes and Hopton to escape local minimas. Finally, the paper also introduces optimized initialization. Essentially, we optimize the initial state to address a problem that a poorly estimated first frame might have a large impact on the entire sequence. The results show that applying a differential simulator yields similar results on standard datasets in terms of joint error and reduction of physical artifacts as in paper 4. Generally though, we note that paper 4 was more capable and robust for noisy and difficult in the wild videos. However, paper 5 is roughly 100 times more compute efficient in terms of function evaluation required than minimizing the loss. This speed up allows our method to be run on a single machine rather than a compute cluster. Compared to prior work, we find that our methods are the only ones to demonstrate results on individual videos while combining support for full body contact. Furthermore, they do not simplify the problem by introducing non-physical residual forces, and they integrate an adaptive physical body model that changes the size and weight based on the reconstructed subject. In addition, paper 4 is the only method to integrate a full-featured differentiable physics engine which allows for gradient-based optimization. Furthermore, our approach to physics doesn't require any training, so it doesn't risk being overfitted to a particular set of motions and doesn't require additional 3D data. The biggest drawback of our methods is undeniably the lack of real-time processing, as even paper 5 takes minutes to reconstruct short motion snippets. It is now time to conclude this presentation and summarize the contributions and conclusions of this thesis. In the beginning, I outlined several challenges in 3D human pose estimation as seen to the left. Part 1 on active human pose estimation concluded that using reinforcement learning, we could instantiate an active observer and that the agent could learn how to select informative viewpoints and even learn when it has gathered enough information. Such an agent could address the issue of depth ambiguities and the ill-posedness of a problem by gathering more information about the subject in the scene. Furthermore, the learned agent could move and explore the scene to avoid occlusions and problems stemming from partial visibility. And finally, it could mitigate viewpoint biases in the underlying pose estimator by moving and selecting viewpoints that were similar to those seen in the training data. In part 2 on embodied visual active learning, we concluded that using RL, we could learn a self-improving agent that requested annotation to its own perceptual model in a data-efficient manner. Using this, we could address the problem of limited and biased training data by having the agent request annotation for novel percepts. This is an important feature as lifelong learning of intelligent systems would allow them to adapt to new environments beyond what was contained in the initial training data. While we studied the problem for semantic segmentation, the underlying idea of how to improve visual perception systems applies to other visual tasks as well. Part 3 on physics-based human pose estimation concluded that physics could be integrated into reconstruction process through the inclusion of a physical simulator, and that by leveraging a state-of-the-art differentiable physics engine, we could significantly reduce the computational cost. Furthermore, unlike many prior works, our method featured an adaptive body model that on the fly adapted to the size, shape, and weight of the subject. This is important as an adaptive body model is a key component for any method that should support complex motions with full body contact. Finally, our physical optimizations are non-learned components that complement any learned kinematic component that might have been trained on biased training data. The universal laws of physics, as approximated by our physics engine, might help the estimation of motions not in the training data by constraining the output to the space of physically plausible motions. In summary, the 3 parts of my thesis proposed different ways to improve visual perception, either through active exploration, active learning, or physical constraints, in ways which complements any improvement to the underlying neural network predictors and their training data. With this, I would like to conclude my presentation and thank you all for listening.